Hello, welcome to this video. Today we're going to do this problem. So we need to show that for all natural numbers n and sufficiently large natural numbers n, there exist infinitely many values k that are natural numbers, such that the digit sum of n plus mk is the same as n digit sum. So basically, it's like an arithmetic sequence. So we're starting with a number n, then n plus m, n plus 2m, n plus 3m, and so on. Show that along this arithmetic sequence, as long as n is for n that are sufficiently large, and that largeness does depend on m, but for n that are sufficiently large, we want to show that in that arithmetic sequence, if we evaluate the digit sum for every term in that sequence, we will hit n's digit sum infinitely many times. Okay, so let's begin. So the simplest way I can think of for two numbers to have the same digit sum, if they have the same digits, but just one has a couple more zeros in it. And the simplest way to achieve that is to just multiply by a power of 10. So you can imagine some number, I don't know, 30,459. If I multiply this by any power of 10, right, 10 to the 0, which is 1, 10, 100, 1,000, they'll just be like adding zeros at the end, which will obviously not change the digit sum, right? So if I like label d as the function of the digit sum, right, this digit sum is the same as if I just remove all these powers of 10, and we're going to use that throughout this proof. So we basically want d of n plus mk is d of n, right? And basically what we want to have is that n plus mk is just n times the power of 10. Because then obviously we'll have the same digit sum. So we're looking for n plus mk is equal to 10 to some, I don't know, gamma times n, right? So we want k such that nk equals 10 to the gamma minus 1 times n. And first of all, notice we do have maybe a couple of constraints on m. So if n could be co-prime to 10, right? Like this number, 30,459. If right, it's not divisible by 2, not divisible by 5. It's co-prime to 10. And in that case, m will also have to be co-prime to 10. Because if that were to be divisible by 2, this is not divisible by 2, and that would be a problem. So now, for this, we're going to assume m is co-prime to 10. Or in other words, the GCD of m and 10 is 1. So that's our assumption. Later we're gonna remove that assumption and prove it without it. But now if we assume that m and 10 are co-prime, then there is Euler's theorem, which is the extension of Fermat's little theorem, which says, so the theorem says, if a and n are co-prime, so the GCD of a and n is 1, then a to the power of Euler's totient function phi of n is congruent to 1 mod n. And mod n. And this totient function is basically the amount of numbers co-prime to n and not bigger than n, right? And there are proofs of it on the internet, but what I care about is not that this is that specific function, is that there is some number such that it satisfies this. So if I take n to be big M and this a to be 10, I get 10 to the phi of m is converted to 1 mod m, and which means that m divides into 10 to the phi of m minus 1, which means there exists some k prime such that when I multiply this by m, I get 10 to the phi of m minus 1. No, minus 1 is at the bottom. Right? And I'm going to label a phi of m as gamma. Right? Because remember, I'm not saying gamma here is a specific number. I'm saying gamma could be any non-negative integer. In fact, it'll have to be positive, right? If gamma is 0, we'll have that k will is 0. But nonetheless, gamma has to be a positive integer. Any positive integer, any one will work. And so I'm choosing it specifically to be phi of m. So I'm going to label this as gamma, and this will be 10 to the gamma minus 1. Right? So now if I multiply by n, I get m times k prime n is equal to 10 to the gamma minus 1 times n. And this I can label as my value k. So I found a k such that m times k is 10 to the some positive integer gamma minus 1, all of that times n. Right? And so first of all, I might be thinking, okay, so you showed that there is some k that satisfies this, but you promised infinitely many values. So hold on, we're going to talk about infinitely many values at the end. For the meantime, we're proving that there exists one value that is a natural number, satisfies this, and then we're going to show that from that we can get infinitely many values. You can think about that yourself if you want to. But for now, let's continue proving. So now we showed that the value k equals, let's see, it's going to be 10 to the phi of m minus 1 divided by m, which if m is coprime, we know that is an integer, times n, right? Because we multiplied here by n. So we showed that this thing satisfies this, and it's an integer. So for m, so if m is coprime to 10, then we're good. We have a value of k that satisfies this. Right? Because again, just plug in this k back and they get n plus n k is some power of 10 times n, which means their digit sum is the same. All good. But what about if m is not coprime to 10? Well, first, so let's clear the board, write what we found here, and continue on without this assumption. Okay, so I wrote what we found out so far. Let's continue. So now we're throwing away the assumption that 10 and m are coprime, which means that there are some powers of 2 and 5, right, because those are the divisors of 10, that are maximal, that multiply into m. So what I dividing to m. So what I mean by that is there exists some powers alpha and beta that are non-negative integers, such that 2 to the alpha divides into n, but 2 to the alpha plus 1 does not, and 5 to the beta divides into m, but 5 to the beta plus 1 does not. Right? Just the maximal powers of 2 and 5 for n. There exist these powers. So what I'm going to say is, well, m has to be 2 to the alpha times 5 to the beta times small m. And that small m, you can think about it for yourself. That small m is co-prime to 10. And just as a quick explanation to why, if it wasn't co-prime to n, then it's divisible by 2 or 5. But if it's divisible by 2, then that's a contradiction to that alpha is maximal. And if it's divisible by 5, then it's a contradiction that beta is maximal. So m is co-prime to 10. Right? A small m is co-prime to 10. So now, what I'm going to show is that there exists a value of k such that 2 to the beta times 5 to the alpha divides into k. I'll show that there exists a value of k such that this thing is true, which means that I would have proven that just such a value of k exists, right? I don't care if this specific number divides into it, I just care if it exists. So I'll show there is one that just satisfies this extra condition. So if this is true, then that means that I can write k as 2 to the beta times 5 to the alpha times some k tilde. But now, what will be n plus mk? N plus mk will be n plus 2 to the alpha times 5 to the beta times, if I plug in k, it's going to be 2 to the beta times 5 to the alpha, now times small m times k tilde. Right? So this is going to be 2 to the alpha plus beta times 5 to the alpha plus beta. That's 10 to the alpha plus beta. So plus 10 to the alpha plus beta times m times k tilde. Right? Okay, so this is true, and now what I'm going to do is just let alpha plus beta, I will set it to t, right? Because I'm going to be using this alpha plus beta a lot, so I'm just going to write it as t. So this is true, and what I'm going to do is set alpha plus beta t, and because I'm going to be using this alpha plus beta a lot, so just so I don't have to write alpha plus beta again and again, I'm going to use t. So this is going to be n plus 10 to the t times m times k tilde. So now I'm going to write small n is equal to the floor of n over 10 to the t. So small n is just big N, but without the first t digits, right? Which means that n is 10 to the t times small n plus the other t digits that we removed. I'm gonna call them a0 up to at minus 1, and so this will be the sum. So that goes from 0 to t minus 1 of ai times 10 to the I. Okay? But now the digit sum of n, big N, is a digit sum of small n plus just the sum of these a's. It's gonna be the digit sum of small n plus a0 plus a1 all the way down to plus at minus 1. Right, so the digit sum of n will be the digit sum of small n plus the sum, so that goes from 0 to t minus 1 of ai. Okay? Okay, but you might say, well, it might be the case that small n is 0, and in that case it's just going to be the sum of these digits. Well, I have here the condition for n, sufficiently large. So if sufficiently, I'm assuming that big N is at least 10 to the t. That's my assumption about big N, because then this number small n will have to be a positive integer. It could not be 0. Right, so here sufficiently large just depends on n. Well, I want big N to be at least 10 to the maximum power of 2 in m plus the maximum power of 5 in m. Okay, but now let's look at what is the digit sum of n plus nk. Let me write this here. The digit sum of n plus nk. Let's see. This is going to be the digit sum. Let's plug this in. 10 to the t times n. I'll split this and then these. So plus 10 to the t times n times k tilde plus the sum as I goes from 0 to t minus 1 ai times 10 to the I. Right? So now this is the digit sum of 10 to the t times n plus nk tilde plus the sum as I goes from 0 to t minus 1 ai 10 to the I. But now, take a look at this. This is a number times 10 to the t. This is a number times 10 to the t, meaning that these are some digits. I know 3, 4, 0, 5, 9, 7, whatever. But then after that come t zeros. And then here I have the rest of the digits that I'm summing that will be at the end of the number, that will be in the place of these t digits, right? Which means that the digit sum of this number is the digit sum of this part plus the digit sum of plus just the sum of these coefficients is ai. This is going to be the digit sum of n plus nk tilde plus this, right? And I'm gonna reiterate again why this is true, because it might be a weird jump. This number is gonna be some digits, and then after that come t zeros. And here I'm adding just what these I'm adding the digits that will be at the end of that number, right? I have some digits and then t zeros, and these determine what digits at the end will be this entire number will have. They're going to be at minus 1, at minus 2, all the way down until a0. Right? So the digit sum of the entire number is just the digit sum of the first t digits plus the digit sum of the rest. And so this is the digit sum of the first t digits. This is the digit sum of the rest. Okay, but now if I want these to be equal, that's the exact same as saying that I want d of small n plus small n times k tilde to be d of small n. So I want d of n plus mk tilde to be d of n. Right, in k tilde I want it to be some positive integer, and small m is coprime to 10. But we did that case already. Right? If I let k tilde to be 10 to the phi of small m minus 1 divided by small m times small n, this works. Right? We showed that earlier at the beginning. So now, to get the actual value k, I'm just going to multiply by 2 to the beta times 5 to the alpha. So k is going to be 10 to the phi m minus 1 over m right? This is not important, and just writing this so we'll have like a final formula. 2 to the beta times 5 to the alpha, where alpha is the maximum power of 2 in m, beta is the maximum power of 5 in m. Small m is big M after I dividing by 2 to the alpha times 5 to the beta, and small n is the floor of big N divided by 10 to the alpha plus beta. Remember, t is alpha plus beta. Okay, so this value works, and I know this value is a natural number because each part here is a natural number, right? This thing is a natural number because m is coprime to 10. This is a natural number, this is a natural number, and because I'm assuming big N is sufficiently large, then this n, small n, again, is a positive integer, a natural number, so this is also a natural number, so k is a natural number. But here, I did not assume that anything about m, right? M could have been not coprime to 10. And so, finally, right, and this k tilde satisfies that this is true, which means that this is equal to this, right? I'm just adding the same number here. I'm just adding to both of these a0, a1 until at minus 1. But this is d of big N, this is d of n big N plus big N times k, and k is this. So I've showed that for this k, these are equal. And so that's pretty much it. One more thing. Like I said earlier, I only proved that there just exists one value of k that satisfies that the digit sum of big N is a digit sum of big N plus big N times k. Why do there exist infinitely many of them? And if you thought about it, maybe pause now and try to think about it. Simple explanation. I can just replace. So I found this value of k. Now, big N plus big N times k is obviously bigger than big N. And the only thing I'm assuming about the sufficiently large thing here is that it only depends on big N, right? I'm assuming it's bigger than 10 to the alpha plus beta, and alpha and beta only depend on n. Which means that big N plus big N times k is also sufficiently large since it's larger than big N. So it satisfies this criteria. And so if we look at the arithmetic sequence that starts at big N plus big N times k, then that sequence will also have another number that its digit sum is the same as the digit sum of big N plus mk. But we just proved that this is the same as the digit sum of n, right? So I'll have another k that satisfies this, so I'll have two numbers. But then I can take the second number that I found and do the same thing and find the third number, right? Because it also satisfies this criteria of sufficiently large. And then I can get a fourth number and a fifth number, and so on. So I can get actually infinite values out of this procedure. So by proving that there's just one, I actually prove there exist infinitely many, which proves what we wanted to prove. And finally, that's it. If you want more content like this, please subscribe to my channel. I'll be putting more interesting problems and things like this in the future. And finally, that's it.